Hi, and welcome to our first lecture in computational finance in this, again, rather weird summer term in 2021 amidst the pandemic. This semester, I will be teaching this class again, actually for a number of times now in a row. Computational finance is meant to be at the intersection of numerical mathematics and finance. I will talk about the different topics that we will be covering in this class later on when we'll have a look at the outline. But at this point, I want to make sure that everyone knows what class this is. This is a class about finance, but also a class about tools from numerical analysis, mathematics and statistics that can be employed in finance and that can be used to get better results, to get faster results, especially when it comes to, for example, option pricing and portfolio optimization. Now, this is the outline of the course. Today we'll start with the course organization and the introduction. As I already mentioned, portfolio theory and portfolio optimization is a large part in this class because, as you can imagine, if you want to optimize a portfolio, you need optimization tools. And this is where we'll take a lot of insights from numerical analysis and move on then to asset models. Asset models are models that can be used to forecast and simulate, for example, prices and returns from certain statistical models, and which can then be applied in any type of financial analysis. Then we'll talk about derivatives and option pricing. Now, this is interesting because if you take a look at different lectures at different universities or also sometimes textbooks on computational finance traditionally is synonymous with option pricing. So what difficult and what complex financial contracts do we have in finance? Well, the most complex ones are usually exotic options. We need mathematical tools for the pricing of these exotic options, and thus you need computational power, you need CPUs, you need more sophisticated mathematical models, and that's why usually computational finance is used synonymously with option pricing and modern techniques to price options. However, in my view, as you can imagine, these other topics also are relevant, just like, for example, portfolio optimization. And later on in chapters 6 and 7, we talk about interpolation and yield curve estimation, because this is a very nice example where you can take very general tools from numerical analysis, interpolation, and you can directly apply it in a financial setting, that is in the estimation of the yield curve. This is done actually frequently done by central banks. Okay, so let's start with the basic course organization. I want to give you some information what this module entails, what the e-learning support is, what the exam looks like, and some basic literature and what I'm trying to achieve this semester. The basic information, I'm probably sure you've already seen this. This is a 6-hour class. We have this 2-hour lecture here, live every week. We have a 2 hours online exercise meant to show some example questions and some mock exams. And we also have a 2 hours online tutorial on financial modeling using Matlab or Octave. Both of these exercises and tutorials are online only, on demand. We are linking those, putting up the links to those classes in the Moodle class as we speak. This is an elective course in our master's degree in business administration, and you can earn 10 ECTS points if you complete the module. The assessment, this is the current status, imagining and hoping that we are all vaccinated by July. And we are able to reopen the university. So the assessment will be a written exam of 90 minutes length If not, as you've probably seen last semester, we'll have some alternative that will probably be a term paper or a take-home exam that you have to do at home. Okay. Now, e-learning, we have a Moodle course and a Moodle website. Actually, if you registered today, I think erroneously there were 2 Moodle websites online, and we will be deleting the one for the exercise, and we are putting up all the information, all the files in that single Moodle course, where you can also download the set of slides, for example. Now, if you're more interested in a little bit of what goes on beyond these lectures, you're free to follow me on Twitter. From time to time, I will be posting something on Twitter that is more related to industry trends or things maybe a regulator has done or something that is going on in research. You don't need this for this lecture, of course, but if you're more interested in financial economics and maybe even a little bit quantitative risk and quantitative finance, just follow me on Twitter. Okay. Now, these lectures, as I already mentioned, they are recorded and they will be uploaded to YouTube without having any problems with your privacy rights. You're not recorded, and we don't have your voices or names or anything up in these videos. But if you are not able to attend one of these lectures, all these lectures will be recorded and they are available here on YouTube. We do have 2 mailing lists. The first one is the general mailing list of the chair's lectures for anything that is related to the lectures. This is sometimes helpful because in some cases, if your faculty, and I'm looking at those people, I think the math and computer science students, they are by now on AlmaWeb, but there are still some faculties at our university that are not using AlmaWeb. So if I have some important messages and I were to use AlmaWeb only, I would miss out some of you. So especially for those who are not registered on AlmaWeb, please subscribe to the first mailing list. And the second one is Jobsbank Fin. Again, you can simply subscribe to this list by clicking on the Jobsbank Fin text. This is a mailing list for job postings and for internships, etc. So just a little bit of help if you're looking for a job or an internship. You can contact me via email. Right now, this is probably the best way to contact me. Schedule a meeting in person in normal times, but now it's probably via Skype. And you can simply go to calendly.com/GregorWeiss and schedule a meeting and a call via Skype. Okay, now let's imagine we have a normal exam at the end of the semester. What will the exam look like? The exam will actually consist of several small questions that will cover the whole course. I'm not a big fan of large questions, so that if you have, for example, if you haven't learned one part of the lecture and the large question is actually taken from that part, the whole exam goes down the drain. So I'm not very much a fan of that. But I try to include all the sections and all the parts of the lecture in the exam. The general formula should be mastered passively. So if you're given a formula, you should understand it. You should understand what it's meant to do. Some very important definitions, models, theorems. Sometimes even they should be you should be able to actively cite those and reproduce those. So strict learning by heart is not necessary. You get a good feeling of what the exam looks like if you have a look at the previous exams and the exercises and the tutorials we have online. Some questions will be discussed in the online tutorial as well, and you can also download the past exams from the Moodle website. And I haven't stressed this enough. You remember that this module is a 6 hours per week class, 2 hours a lecture, 2 hours online tutorial, and on-demand tutorial for exam preparation, but as you will shortly see, most of the algorithms and most of the things we are looking at in this class will be highlighted and exemplified using Matlab or Octave. Matlab is a math program. Octave is the open source variant of Matlab. If you don't have Matlab, it's virtually the same. And you don't need any programming skills for this class or for the exam. But if you're more interested in this, you're free to take the online tutorial for Matlab Octave programming to get a better understanding of the programs. Okay. Now we have a number of textbooks that can be used in addition to the slides. The first disclaimer I have to give you is that you don't need any of these textbooks. The set of slides is actually enough to pass the exam. Everything should be on the slides. However, if you want to read a little bit more, if you are very interested in this topic, most of the lecture is actually based on these two books, Brandy Mate and Albrecht Maurer, Numerical Methods in Finance and Economics, and Investment und Risikomanagement. This one is in German. Now, one has to see that the first one is quite expensive. I think it costs about 120, 150 euros. We might have one copy in the library, but you don't need to buy this. Maybe you can find some extracts on the internet. There are some other books which are actually quite nice. For example, Applied Computational Economics and Finance by Miranda and Fackler, and also Paul Wilmot on quantitative finance. Now, Paul Wilmot is a very interesting person. He used to be, I think, a university lecturer at Oxford. I think Oxford, yes. He then moved on to the industry and became a quant in London for several banks, I think. Also managed his own hedge fund and founded Wilmot, a journal that is specialized on issues related to quantitative finance. And this this rather a three-piece compendium. This is not just one book. I think it has many parts. This is a huge piece of work on quantitative finance, and it's called Paul Wilmot on quantitative finance. So this is, I would say, for the connoisseur who's really interested in quantitative finance, and you can read about anything in this book. Okay. Now let me just get my pointer here. We will also upload some data sets via Moodle, and you can then try to implement those programs via those data sets. And again, we're using Matlab/Octave in this class. You can also use Mathematica, R, or any other mathematical statistical standard software. However, in this class, I wanted to show you Matlab. And again, Matlab only comes at quite a high fee, I think, or at least the student version is a little cheaper, but still you need to buy it. Octave is the open source variant that you can download for free from the internet. Okay. Now, what do I want to achieve in this class? First of all, I want to show you and highlight the problems that you can encounter when you're doing numerical calculations in finance. Now, up to this point, I think, in most finance lectures you've probably taken, it has always been the case that we professors argue, you have this model, you might have some data, but if you understand the model, the rest is only inserting numbers into the model, and then it will all work out nicely. This is not so true, as some of the examples in this very first lecture will show. Even if you have a correct model, even if you have data that are error-free, you can still run into numerical problems simply because it's a computer, it's an approximation in some cases, and I want to give you a good understanding of some of the practical issues you might encounter when implementing those theoretical models from finance. And I think the most important topics then obviously are portfolio optimization, asset models, solving equations, optimization again, Also a little bit of matrix decompositions. You sometimes need those in between. Term structure models, interpolation, and option pricing. And again, I mentioned that option pricing is often used synonymously with computational finance. So we are only looking at a small part of this type of computational finance, because I want to show you a little bit more about portfolio optimization and all those other topics, like, for example, term structure models. Okay, so this is the introduction. This is the course organization. And let me now start with the introduction, a short introduction to Matlab Octave, and some motivating examples on why we should be looking at computational finance and numerical mathematics in the first place when implementing financial models. Now, again, the course name already hints at the fact that we are going to look at the intersection of finance, financial mathematics, and numerical mathematics. What is numerical mathematics, or sometimes numerical analysis? Now, in mathematics, if you're not studying math, it's quite simple to look at the main areas of mathematics. It's usually algebra, then calculus, analysis in German, and maybe statistics, a third large part, and then numerical analysis, numerical mathematics. What is numerical mathematics? It's the part in mathematics that starts by taking a model and you want to calculate the results of this model or of a function by plugging in numbers, real numbers, and then you might encounter problems like you have to round numbers. Maybe you need a higher precision. You suddenly get only approximate results, or you find out that there is no model to calculate a certain mathematical object, like a function value or the solution of an equation, for example. And then you're not interested, or you're interested ideally in the exact solution, but you might know, okay, I'm not able to find the exact solution, so you need approximate solutions. You need approximate values, and this is where numerical methods are used. Now, why is this related to finance? Well, it's the increasing complexity of financial products. It's the increase in financial products and structured finance, like, for example, options, equity options, etc. And because these financial products have become more and more complex over the years, this part in finance is actually nowadays called financial engineering, because you need skills like an engineer, you need math skills like an engineer to take those complex financial products and recombine them and analyze them in a different way to get an even more complex financial product. That's why it's called financial engineering, and financial engineering takes its hints from financial mathematics, but also numerical analysis. And even though I've talked a lot about numerical mathematics by now, this is not the main focus. The focus of this lecture is finance. It is the finance models that we'll be looking at, and we'll be selectively taking those hints and those models from numerical analysis as we go through the lecture, and only at these places where we need those tools. So this is not really a math lecture. No? Okay. And you don't need any prior knowledge. Everything I'll be presenting in this class will be presented in such detail that you should understand it, even with a very basic understanding of mathematics, as any econ or business grad student should have. So actually in this very first lecture, we'll start with some motivating examples, actually basic problems from numerical analysis, where you immediately see with very simple calculations on a computer, you need more math and you need more tools if you are going to implement some financing tools and financing models on a computer. So actually it will start with exactly this problem. Numbers on a computer usually have a finite representation, so even a very long, even a very large number at some point has to be rounded off, and this will introduce a rounding error. And we'll also see some general other numerical problems that can arise in a financial context. Okay, so we start with Matlab Octave, and if you haven't done this already, I would suggest that you, well, after the lecture, or you can stop the video now, that you install Matlab or Octave. Matlab is a very powerful tool. It's based on, I think, C and Fortran. It uses some very standard libraries from numerical analysis. And we will learn most of the syntax of Matlab or Octave on the fly, so you don't need to take the Matlab course right now. As you can see in just a couple of minutes, it's very simple at the very start. You probably don't see much on this slide. It's a very bad screenshot, but this is what Matlab looks like. You have a window where you can enter your commands. You have a window where you can see the defined objects like vectors, matrices, numbers, and you can also see the current folder. So very simple tool, and you can look up all the different commands on the internet. Okay, so let's start with some motivating examples. Perhaps the best known model for pricing a European call option is the Black-Scholes model. We will be talking about Black-Scholes in detail later on. Maybe you've taken the financial risk management class in our bachelor's degree, then you should know the Black-Scholes model. At this point, it suffices to say, if you have no idea what the Black-Scholes model does, it suffices to say that it is a model that yields an arbitrage-free price for an option contract, a European call option. Now, let's start with an option. An option is the right, but not the obligation to buy or sell an underlying, usually a stock. So, for example, you could say European call option. It's called European because you can only exercise this option at the very end, at maturity. So European call option is the right, but not the obligation to buy, it's a call option, to buy an underlying stock at maturity of the option contract. And the Black-Scholes model, under very specific assumptions and in a very, actually very fancy way, it shows what this option contract should be worth, what the fair price of this option contract should be. And in the special case that the share pays no dividend and the share price of the underlying satisfies some conditions, most notably that the share price follows a certain statistical distribution, we get an analytical solution for the arbitrage-free option price. Now, what is an analytical solution? For example, if, let me just get, where do I have this? Yes, here. For example, if you have a system of equations, like for example, x equals, let's say, 5 plus y, and 4 minus y equals 2x, or something like that. Now, from school, you know, you have two equations, you have two variables, and you are most likely to find a solution that is exact. Yeah? X equals yada yada and y equals yada yada. Now, this is an analytical solution. It's the exact, it's the right solution. It's eine analytische Lösung in German, also die exakte Lösung. Now, the Black-Scholes model gives you exactly this. Under certain assumptions, you get the analytical solution. But what we are more interested in this case is actually what kind of numerical problems could arise. So this is the Black-Scholes formula. Under these assumptions, we get the arbitrage-free price of the option contract, the European call, by C0 equals S0 times n of d1 minus k times exponential function of minus r times t times n of d2. d1 and d2 are these two arguments here. You don't need to remember this at this point. If you've taken a class on derivatives or financial risk management, you probably know this. But this is the current stock price, S0. K is the strike. So that's the price at which you can, or for which you can actually exercise the option. Exponential function of minus RT is nothing but the discount factor, a continuous discount factor, and n is the distribution function of the standard normal distribution, also die Verteilungsfunktion der Standardnormalverteilung. And D1 and D2 are simply two arguments you have to plug in. So you need the current stock price S0, the strike, the risk-free interest rate R, and the stock volatility sigma. And by plugging in those parameters into D1 and D2, you can plug it into the equation for C0, and what you get is the arbitrage-free price of a European call option. So that's the Black-Scholes formula. Now at this point you would think this is cool because it gives you an analytical solution. There is no rounding error, there's no approximation. This is under these assumptions, and that's what we assume. If those assumptions are true, this is the one and only true exact price. Problem is, if you take a closer look, the Black-Scholes formula gives you an analytical solution. For exotic options, we don't have this, so we need approximations after all. However, if you take a look at this, n of D1, the distribution function of the standard normal distribution, this is actually given by this formula, 1 over volatility times the square root of 2 pi, and so on and so on, and you have this integral here. And you might remember this from school. Integrals, they can get nasty from time to time. And actually this one is. So you need to calculate this value, this integral. Problem is, even though this is the analytical solution for C0, there is no analytical solution for n of D1. So you need to approximate this, and this is where some problems start. So actually, to come back to this, you need numerical analysis to calculate this integral. That's a problem. Okay. Now, as we will see, some methods are more suitable for special problems than others. In some cases, you have two algorithms at your disposal, and one is maybe faster. The other one gives you a better solution, and you have a trade-off between computational complexity, speed. You have a trade-off when it comes to the exactness and the error of your algorithm, and also what we'll see later on of the condition of the problem, that is error propagation and maybe even a worsening of errors. So you have a slight error that is introduced into the data, and the algorithm actually boosts this error to extraordinary proportions. So this can all happen, and it will actually start with the representation of numbers in a computer. So we'll start with this very simple example, and this is also the first time you will see some Matlab code. So we are looking at the simple expression 9 times 8.1 plus 8.1. So by the way, we'll be using the English style, and decimal places will be shown by a point and not a comma as in German, because this is also how it's done in Matlab. So if you insert 9 times with a star, 9 times 8.1 plus 8.1, you get the answer in Matlab 81.0000. Looks good. As you can see, this is simply 10 times 8.1, so we are expecting 81. But remember, here, for some reason, we are also given several zeros at the end. Okay. Now, next, we are looking at the Matlab function fix. Fix rounds the argument to the next natural number. So, for example, fix 4.1 is 4, and fix 4.9 is also 4. So we are rounding down. Again, we are now applying fix to the previous term, and we get a rather surprising result. For example, fix of 9 times 8.1 plus 8.1 gives you as an answer 80, even though before we saw it's 81.0000. So what is happening? Question now is, why does fix of 10 times 8.1 why does it not return 81 but 80? And to see this, we need to change the display format in Matlab, and we are now saying, okay, format long, which means that instead of 4 decimal places, we now get, I think, 60. Okay. And if we compute 9 times 8.1 plus 8.1, the answer is actually not 81.0000, but it's actually 80.999999986. And then, if you now apply this function fix to this here, then it's clear that the answer will be 80 and not 81. So this is a very simple example that shows a basic problem when calculating with computers. Numbers in a computer are first of all represented internally on the CPU by a floating point representation based on the binary system. So the computer can only work with ones and zeros. And a number like 8.1, which seems very simple and easy in the decimal system, is actually not so harmless in the binary system. Because in the binary system, there is not a finite representation of 8.1, but actually it's infinite. So the binary number for 8.1 is infinite, and the computer doesn't work with infinite numbers. At some point, it has to cut off this infinite number. And this is actually happening at this point, and you can see that my computer, back when I wrote those slides, had a precision of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, actually 14 decimal places. So already after 14 places, there is a cutoff error. And this is because 8.1 is an infinite number in the binary system. So we have a rounding error or a cutoff error. A second example that highlights how a very simple and a very easy seeming problem and algorithm can actually cause large and huge problems on a computer. We are looking at error propagation, and we are considering the example of a linear system of equations, ein lineares Gleichungssystem. H times x equals b. Matrix H and 2 vectors x and b. X is the solution, and b on the right hand side could be 1, 2, 3, 4, 5. And H is called a Hilbert matrix if it has this very special form. You start with 1, 1/2, 1/3, and so on, 1 over n, 1/2, 1/3, 1/4, and so on. And if this matrix has this structure, it's called an n-dimensional Hilbert matrix, the n-dimensionale Hilbert matrix. It's still a linear system of equations, and from your math exam in algebra, in linear algebra, you should all be able, even in high school, you should all be able to solve a system of linear equations on a piece of paper. Now see what happens on a computer. We are taking a very simple example, and in a way we reverse engineer this, because we say that the solution is 1, 2, 3, 4, 5, 6, 7, 8 up until 9, and we are constructing this vector b, and we want to see how MATLAB works and if it's able to retrieve our original solution, which we know is 1, 2, 3, 4, 5, 6 until n. So first of all, we define the Hilbert matrix. H equals Hilb 20, so it's a 20-dimensional Hilbert matrix. As you can see from the comment, the semicolon helps you in MATLAB, because in this case, the display, oh no, actually the result will not be displayed. We don't want to see this huge Hilbert matrix on the screen, so simply, instead of just pushing return, enter semicolon and then return. X is 1, 2, 3, 4, 5 until 20, and by using 1, double point 20, this creates a vector. The apostrophe leads to the transposition, so you're transposing the vector. It used to be, I think it used to be like this. It's a horizontal vector and then it's reversed in or transposed into a column vector. And then b equals h times x. So actually this vector b is constructed in such a way so that with this Hilbert matrix we get the solution vector 1, 2, 3, 4, 5 and so on. And then let's take the backslash operator in Matlab, because if you write h backslash b, this is the operator, this is the function in Matlab that solves a linear system of equations. Okay, so what is the result? The answer is we are expecting 1, 2, 3, 4, 5, 6 and so on up until 20, and as you can see the answer is 1, 2.0011, 2.9574, 4.7031 and so on and so on. And here, as you can see, we are expecting 11 and Matlab's answer is 202, so it's completely off. Okay, in this case it's interesting to see that this is not due to the actual algorithm, but it's due to the fact that the problem itself, using a Hilbert matrix in a system of linear equations, using a Hilbert matrix makes the problem badly conditioned, schlecht konditioniert in German. We'll later on see what this means, but intuitively it describes the problem that a mathematical algorithm or mathematical problem itself leads to a large error propagation. So you have a small error and it's propagated and actually increases in size simply because of the condition of a problem. And this does not always have to be the case. There are some examples in which a problem is poorly conditioned, even though, for example, a matrix is regular. It's not because the Hilbert matrix is close to being singular, so especially not invertible, but this is a common problem with the Hilbert matrix. Okay, so let's talk a little bit about some basics in numerical analysis. We've already heard, for example, the condition of a problem, and we'll start with number representation and rounding errors. This is the problem we already saw with the 10 times 8.1. The computer works in the binary system. We, however, work with the decimal representation. So our numbers, like 1492, they are represented by 1 times 10 to the third power plus 4 times 10 taken to squared plus 9 times 10 plus 2 times 10 taken to the 0th power, so it's just 2. Now the decimal places can also be depicted in this manner. For example, 0.42 is just 4 times 10 taken to the power of minus 1 plus 2 times 10 to the power of minus 2. Then in this decimal representation, we can see that some numbers obviously do not have a finite representation. For example, 1/3 is 0.3. Okay, so it's an infinite representation, so this number, 1/3, would cause some problems in the decimal system. And it looks different on a computer when you switch to the binary system. For example, 21.5 has this representation in the binary system, 10101.1, and a seemingly harmless number in the decimal system, like 7/10 or 0.7, suddenly becomes quite harmful in the decimals, in the binary system, sorry. So because the finite representation of 0.7 now becomes 0.1 and then period 0110 in the binary system. So some cases, if you are taking numbers to the computer, it might have a finite or sometimes an infinite representation in the binary system, and then you will have a cutoff error. Numbers need to be cut off, you will have a rounding error, and this leads to a rounding error. Okay, next, it might be that you encounter some mathematical terms that are already given as an infinite sum, and they need to be made calculable for the computer. And the best example is probably the exponential function. The exponential function, one way to define it in real numbers, is the infinite sum of k equal to 0 until infinity of x to the power of k divided by k factorial. And to calculate the exponential function, even your calculator, you will have a truncation error. At some point you will need to cut off the last parts of this infinite sum, and then you will have a cutoff or truncation error. And closely related to this error is the phenomenon of cancellation. In German it's called Ausolution. It describes the loss of accuracy due to the subtraction of almost equally big floating point numbers. So if you have two numbers that are very close to each other and you subtract those, for example, a equals to 2.345678 and b equals 2.346789, you would expect the exact solution of 0.001111. But if you only use a computer that has an exactness or a precision of 2 decimal places, then you would get the result. Again, you would cut off here. Then the solution would be 0. And what happens in cancellation is, if you now take the relative error, so the error relative to what you're expecting, the relative error could be quite high. And this is called cancellation every time you have two numbers that are almost equal and you subtract those numbers from each other. Okay, so the absolute error does not seem to be very big at first, but the cancellation of leading places results in a disproportionately high relative error. Now we need some properties of algorithms and mathematical problems to see which algorithms are well suited and which algorithms are not so well suited for our purposes. And I guess the three most important properties are stability, convergence, and condition, and we'll be discussing these on the next slides. So what is stability? Now we want to start very general, meaning that our numerical problem is actually a function f of x. We have input data x, and we want to calculate the exact solution, ideally the exact solution of y. So plugging into input data x into the function, you get your result y, and the actual input data are usually disturbed, so that you're not using x, but you're actually using x bar. X plus delta x. Delta x is the data error. So you have a slight data error, could also be negative, but then you only have to switch here delta x. And you're inserting x bar into your function. Now, what is stability? The exact solution of the problem for disturbed data is given by f of x bar. Remember, garbage in, garbage out. If the algorithm, if your mathematical problem is perfect and you are inserting faulty data, don't expect to get the result y. You are expecting f of x bar. So you expect your algorithm to work properly, but you are expecting a different result than y, obviously, because you have different input data. Now, an algorithm for the problem will provide a solution y star. And numerical stability is a property of an algorithm, and it's called stable if the relative error fx bar minus y star as a norm could be, for example, the absolute value of this difference divided by the absolute value of fx bar has the same order of magnitude as the machine epsilon. And the machine epsilon is actually defined by this here. You have a number x. If you round it and you're looking at the relative error, so here we have the absolute error, and if you divide it by x, you get the relative error. If the absolute relative error of the computer is still smaller than epsilon. So the machine epsilon is actually a lower bound for the precision, for the rounding error. So an algorithm will be called stable if the relative error of this algorithm has the same order of magnitude as the machine epsilon. What does it mean? It means that you have an input data error, you have erroneous data, you're putting in the data with an error, And this is the difference here. This is the difference, what we are expecting ideally of the algorithm with erroneous data, and what are we getting relative to what we would like to see. So that's numerical stability. Next, let's talk about numerical condition. We say that a problem is well conditioned. So the following relation is valid for a numerical problem with a relevant norm, usually absolute number. So we are looking at now our ideal solution, f of x, no data errors, and the algorithm works perfectly, minus what the perfect algorithm would yield if we have an input error in our data, relative to what we are expecting with no data errors. And this is smaller or equal to condition number, we call this a condition number, sigma, times x minus x bar divided by x. So what does it mean? Imagine you have one number, let's say 1. That's the true input. We have a slight input error, and we are not inserting 1, but we are inserting 1.2. So this would mean that if you take this here on the right hand side, this would mean that we have a 20% input error. So the input data is off by 20%. The question now is, if the result, the ideal result is, let's say, 7, do we get a result that is 7? Do we get 7.14? Do we get 7.20? Do we have a relative error of 20% or maybe 10% or maybe 50%? And this is governed by the condition number. The condition number leads to might lead to a situation where we have a 20% error in our input data, and the algorithm makes it even worse, and in the end we have maybe a 50% data error in our result. That's the condition number. It's irrespective of the algorithm. Actually, it's effect of the mathematical problem, as we've seen with the Hilbert Matrix. Okay. One example, a different example for the condition of a mathematical problem. You should probably all know what a polynomial is. And we look at the following standardized polynomial equation in the so-called monomial representation. We are using monomials, monome, which is just x squared, x to the third power, x taken to the power of 4, and so on. So this is x to the power of 8 minus 36 times the x taken to the 7th power, and so on. And we are interested in the roots, in the zeros, the Nullstellen of this polynomial. And we calculate the roots using the Matlab function roots. And as you can see, we already know that this is probably a slight error at the 16th decimal place, but it looks pretty good. And actually, this is the way I constructed this polynomial. I simply took, I can write this down. I simply said, okay, p equals x minus 1 times x minus 2 times x minus 3. So by using all those linear factors, I constructed P1, actually. I called this P1. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Those are the roots, the zeros of this polynomial. Question now is, what does Matlab do if we insert a slight error in our input data? So let's see this. What I'm doing now is I'm changing the second number here, minus 36, to minus 36.001. Slight error here. A very tiny error, and see what happens. 1, okay, still correct. 2, still okay. 2.99 instead of 3, so the errors start to pile up. 4.16 instead of 4, 4.57 instead of 5, 6.49, 6.49, 8.27. So the numbers are all off. And we can see we have a very tiny error in our input data, and what happens is the errors blow up in our result, and this is actually a problem that solving for the roots of such a polynomial in this representation, in this monomial representation, is badly conditioned. Okay, so the small error in the input data strongly influences the quality of the solution, and this is not a characteristic of the algorithms used by Matlab. This is actually a problem of the mathematical problem itself. For example, with roots, never use the monomial representation. You should use a different representation, for example, Chebyshev or Lagrange or some other representation. This is much better suited. We'll come back to this later when we talk about interpolation. So this is one problem. Now, if you look at this here, you might see that this is a weirdly looking number. And this is actually not a real number. This is a complex number, and a komplexe Zahl. What is meant by a complex number? Complex numbers are actually a very large field in mathematics. You look at the field R squared of the real two pairs, and you define two numbers, a, b, and c, d. And for those two numbers, you define a sum, ab plus cd equals a plus b and c plus d, as well as a product, ab times cd equals ac minus bd and ad plus cb. Using these operations, you can actually show in mathematics that what you get is a field of numbers. We call these numbers the complex numbers, that actually includes the real numbers. And because of this part here, you can write those complex numbers either as tuples ab, or you simply write a plus I times b, and I is the so-called imaginary unit, die imaginäre Einheit der komplexen Zahlen. Okay, some important characteristics. Very crazy to see that if you take this number I, which is not a real number, it's a complex number. If you take I squared, you can calculate this. You simply have to add, insert it into the product here. You can see that actually the result is -1, which is the first surprising result in the complex numbers, that you have a number and the square product of this is a negative number. The real numbers form a real subset of the complex numbers, and the so-called fundamental theorem of algebra. Every polynomial of level n has n complex roots. So in the real numbers, for example, x squared plus 1 equals 0 cannot be solved. However, in the complex numbers, you can always find the roots, and you always have n roots. And these two solutions here, 6.4999 plus 0.7293i, this is a complex number. And the problem now you can see here is that, first of all, Matlab does not only give you a solution that includes an error, Matlab also needs to leave the real numbers and go into the complex numbers to find any solution. So this is a serious problem when you again, remind yourself, you're only interested in the roots of this polynomial. It doesn't even have to do anything with finance, but as you can imagine, we have polynomials everywhere, and this is a huge problem. So we have stability and the condition of a problem. And now let's talk a little bit about the order of convergence and complexity. This is basically about speed. Now, many mathematical problems can only be solved by iterations, by an iterative procedure, and you have an approximate solution xn, and you're interested in finding a slightly, or maybe even a much better solution, xn plus 1, that is calculated, and such an iteration sequence should always converge to the intended solution x star. That is, you have your iterations, first solution, second, third, and so on, xn, and at some point xn converges to the true solution x star. Then the order of convergence, I mean, this is a prerequisite. We are interested in algorithms that always converge. That's the ideal situation. Then you're interested in the order of convergence of the algorithm, that is the speed. So the order of convergence is defined by saying, for example, that an algorithm is at least of linear order of convergence if the following holds for a constant c smaller than 1 and a natural number n. xn plus 1 minus x star as an absolute number or as a norm is smaller or equal than c times xn minus x star. Meaning what? The difference between the best solution xn and the true solution becomes smaller, and if it's smaller than, let's say, c times the previous difference, then we say it has a linear order of convergence. Now we say the order of convergence is quadratic if you have a very small difference, xn minus x star, you square it, and then it gets even smaller, and multiply it with this constant c smaller than 1, so it again gets smaller. And if the next difference, xn plus 1 minus x star, is smaller than this on the right hand side, then the speed of convergence is obviously much higher, and we call this order of convergence quadratic, and you can go on from there. Next, we also distinguish between local and global convergence. If we have an iterative procedure, if, for example, you're trying to find, let's say we have a plane here, and we have a local optimum here, and we have a second local optimum here, then it could be that an algorithm starts out here and it converges to this point. If the algorithm starts out here, it might be that it gets close to this one, but then it converges to this one. So if these 2 points, if these are equal, for example, if they are both minimal or if they're both maximal, we have local minima and local maxima, local optima in general. The question now is, if, for example, if there is a third point here, that is the global optimum, does our algorithm always find this point? Does it lead here? Is it globally converging? Or if we start here, does it maybe go to this point, to this local optimum? So if the convergence of an algorithm is only given when the start value is within a possibly small interval around the intended solution, the optimal, we speak of local convergence. If our algorithm always converges to the true solution x star, we call this a globally convergent procedure, and we need to show for some algorithms whether they are locally or globally convergent. And this is obviously a nice feature. Simple example for the convergence is the Newton iteration. An algorithm, the Newton iteration is an algorithm for the solution of a nonlinear equation, and the iteration is given by xn plus 1 equals xn minus f of xn divided by the first derivative of f at xn. And we calculate one root of the previous polynomial with the Newton iteration, and as a start value we choose x0 equals to 7.5. So let's see what happens. We define our polynomial with a slight data error. So this is the data error, remember. x0 is 7.5. p1 bar is polyder of p1. What is polyder? Polyder is a standard function in Matlab that calculates the coefficients of the first derivative of a polynomial. So what p1 bar is, this is again a polynomial, it's a vector of coefficients, and it's simply the coefficients of the first derivative of p1. Then x1 is, this is the Newton iteration, x0 minus polyval gives you the value of a polynomial, in this case of p1 at x0, divided by polyval of p1 bar at x0. And the solution x1 is 6.9765. And we continue this, and as you can see, after only 3 iterations, we already get 7.000001 as a possible solution for the root 7. So pretty good. Okay, so after 3 iterations, we get a relatively good approximation However, the Newton iteration, sometimes also called the Newton-Raphson algorithm, is locally convergent. So it's no surprise that by starting at 7.5, we are moving into the direction of the root 7 and not of the root 5 or 1, for example. But it has quadratic order of convergence, so it is very fast. It could have also diverged. It could have also gone to a different solution, or maybe to a local optima, which would have not been very good. So this is the Newton algorithm. And last but not least for today, let's look at a very simple example with fixed income products from finance. So we start with an ordinary cash flow of a coupon bond, and it's given by 0, 8, 8, 8, 8, 108. So very simple cash flow, and we don't know the price yet, so this is 0. And after one period, we get 8 interest, 8, 8, 8, and then we are being paid back the 100 notional and 8 interest. And we want to calculate the present value of the series of payments. So we form our small program. PV equals my PV var of cash flow and R. We first get the number of periods, n equals the length of our cash flow vector. We then determine the vector of discount rates. We have the interest rate R, which is a variable that is given to this function PV. Oh no, actually my PV var is the function name. And the discount factor is again a discount rate vector is the vector df, and it equals 1 point slash 1 plus r point hat 0 double point n minus 1. And these operations with a point, they work on the desired operation, in this point, for example, dividing those elements from a vector element by element. And also, in the end, dot x and y corresponds to the scalar product x times y. And what I'm doing here is simply I'm calculating the present value. So, for example, for an interest rate of 5%, take those 5% and then you form 1 divided by 1 plus 5%. Next, 1 divided by 1 plus 5% squared, and so on. And we get all those different discount factors. And then we can calculate the present value simply by by multiplying the discount factors with the different cash flows. Now, in the next step, we want to determine the internal rate of return for this cash flow stream if we assume that the series of payments nominal value is 100. Now, the internal rate of return is, of course, given by the finite sum of the cash flows divided by 1 plus r taken to the power of t, and it has to equal 0. In this case, we get the internal rate of return r. Now, we already know we have the cash flows, and we need to solve for the roots of this polynomial in the end, and we can use the function roots for this. So let's do this. Take the cash flows, minus 100, 8, 8, 8, 8, 108, and we calculate the roots of this. Zt equals roots of, we have to flip it from left to right, because in this case, polynomials in Matlab start always with the monomial of the highest order, so x taken to the power of 8, for example. So to flip it, this is what we do with flip LR, flip from left to right, the cash flows, and you can see the answers are actually 4 numbers in the complex numbers, and 1 real example, 1 real number, and this is a discount factor. If you reverse it now into an interest rate, we can see that it gives us the 8% return. Not a big surprise, because if the price is minus 100, then of course the internal rate of return needs to be 8% with a flat interest rate and flat yield curve. Okay. You could also think of just taking the results whose imaginary part is exactly 0. So this is what we've done here, and we've neglected all those other results. In some cases, this might lead, however, to some problems. For example, in this example, take x minus 100 taken to the power of 3, and this is the polynomial x taken to the third power minus 300x squared plus 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 equals to 0. And as you can see, we have 3 zeros. actually we have 1 0 with the order of 3, 100, also eine dreifache Nullstelle. And if you now take the function roots again with this monomial representation, you can see that you're actually not seeing that this is real root 3 times, but actually you would think that, okay, these are 3 distinct roots, and this is misjudged by Matlab. Okay, so this is everything for today. Thank you very much for your attention. Next week we'll continue with portfolio theory, some basic results from Markowitz's portfolio theory, and then talk about the numerical solution of linear equations, which we will be needing in our discussion of how to solve this, how to optimize this, and of course in many other settings in finance. I will now stop the recording and we can answer your questions. But until now, thank you very much for your attention, and see you in the next week or the next video.